All right, hello, welcome. In this video, I'm going to be doing a quick recap of Cal BC Unit 4, reminding you of the stuff that we did as you prepare for the test. Big thanks to number 510 in my third period who suggested this. I'm always looking for new ways to, make my calculus course a little better, and I think that this is definitely going to be one of them. Okay, so just to review, in the biggest of pictures, then I'll kind of like dive deep into each item individually. Okay, in Unit 4, we were studying like implicit differentiation, really is what it was. Whoops. Okay, implicit scenarios. And so just to kind of remind you of what an implicit scenario is, that was where we were like letting different variables commingle freely. Okay, it wasn't always y equals and then something involving a bunch of x's after that. So, an implicit scenario is something like x plus sine of 2y equals xy. Something like that, right? And so we started off with the first lesson was implicit differentiation, and that was just us taking derivatives implicitly, finding slopes of tangent lines, things like that. Okay, and so really the idea here is that implicit curves, they may not be a function in their own right. Like this thing, I highly doubt you can solve for y as a function of x. Doesn't seem very likely, especially with the x, y, and the sine of 2y. Algebraically speaking, it doesn't sound like we're going to be able to really solve for y. Okay? And as a result, sometimes these things can do, have weird things going on with them. Like, a vertical tangent, not a function. Or even it could like loop back in on itself, something like that. Okay? These are things that can happen with implicit curves. And so just, for a quick example, what this mostly was, finding dy dx, or finding the second derivative given dy dx implicitly. So, for example, maybe this is actually probably a pretty good example. So, for example, what we did is we started with some sort of, equation like this, and what we were going to do is say, well, we're going to take the derivative of both sides of this equation with respect to x. So the derivative of x with respect to x is 1, but the derivative of sine of 2y is going to be 2 cosine 2y. But since we're taking the derivative with respect to x, we're going to just consider y as a function of x. So we need to, for the chain rule, multiply by the derivative of y with respect to x. And then over here, x times y, it's a product, so we need to observe the product rule. We need to say that we're going to take the derivative of x with respect to x first and leave y the same. Okay, so it's 1y, plus leave x the same and take the derivative of y with respect to x. Okay, and then if we had to solve for dy dx, which is very often the case, okay, we would collect everything with the dy dx to one side. So that would be, 2 cosine of 2y dy dx minus x dy dx. And then we collect everything that doesn't have dy dx to the other side. So it'd be 1y minus 1, so just y minus 1. And then I can solve for dy dx by factoring out the dy dx and then dividing by what's left. So it'll be y minus 1 divided by 2 cosine of 2y subtract x. Okay? And then if they gave us a point that was on the curve, and let's see, do I know of a point that's going to be on there? That doesn't seem... Maybe 0 and... Nope. Maybe 0 and pi. Yeah, 0 and pi. Yeah. So if they asked us to find the slope of the tangent to that curve at the point where x is 0 and y is pi, because sine of 2 pi is 0, equal to 0 times pi, is going to be, all right, dy dx at x equals 0 and y is pi is going to be, all right, pi minus 1 over 2 cosine of 2 pi, so that's 2 times 1, minus x is 0. All right, I lost myself a little bit, got a phone call. But that's what happens when we plug in a point. We can get a slope of a tangent line at a particular value on a curve. Okay, and so I think that's about all I had to say about that. You know, obviously there are other things that can happen in implicit differentiation I just showed you, but I think that'll be a good, you know, just reminder of what we did there. Okay, in 4.2 we did linear approximation. Okay, and linear approximation was where we had some kind of function. Maybe it was defined implicitly, maybe it wasn't. You know, who knows. And we wanted to look closely at it and, you know, determine based on its tangent line, maybe it was a difficult to compute function like a logarithm or a square root or something. And we wanted to approximate this value. And it was way easier to use the tangent line. And we know that near the point of tangency, you know, tangent line is not a bad approximator, right? So, what was I going to say? Okay, so what we really did was we said, you know, suppose we determined that this, you know, this point was 4 and -5. The slope was, I don't know, looks like a fifth, or maybe I'll make it a sixth. All right, so we write down the equation of the tangent line. Y minus -5 is equal to 1/6 of x minus 4. And then it's always like, okay, you know, this is the graph of g of x. And it says something like, okay, give me an approximation for g of, let's say, 3.94. Yes. Okay, so g of 3.94 is going to be approximately equal to -5 plus 1/6 of 3.94 minus 4. And hold on, let me erase that. I needed a -4, right? So get that out of there, -4. Okay, and then I'm going to, you know, do some arithmetic. And of course, in a free response setting, this is a safe place to stop. But what's going to happen is -5 plus 1/6 of -0.06. So it'll be -5 minus a 0.01, and that'll be -5.01. Okay. Based on the fact that, okay, you know, I'm going to have to ask it backwards because we're starting from a drawing, but oftentimes we'll ask about, is it an overestimate or an underestimate? And that consideration is the same question as, is the curve concave up or concave down? Okay, and so if I said, you know, based on this drawing, you know, what's the sign of the second derivative? Okay, because it's an underestimate, I know that the second derivative has to be positive. And if the second derivative is positive, I know a tangent line approximation is an underestimate because concave up, really what that means is the tangent line sits below the curve near the point of tangency. Okay, I think that's about all I've got to say about linear approximation. All right, and then the last thing we did was, for the past couple of days, we've talked about related rates. And so then we had 4.3 and 4.4 related rates. Now this was always like kind of something changing with time, like a sphere is getting bigger or a cube is shrinking, something like that. And what we're going to do with these is we're always going to kind of start with a geometry formula and take the derivative implicitly with respect to time. Okay? So, if we had, I don't know, I'm thinking of a situation that would be pretty easy for me to work through quickly. Suppose we had a square. And it was expanding. And the perimeter was expanding let's say at a rate of 1 inch per minute. Okay? And, you know, I might ask you, what is the rate of change of the area of the square when the side length is equal to 2 inches? Okay, So what we're going to have to do is we're going to have to work with some geometry formulas and take the derivative of them with respect to time. So this is x, and if it's a square, then these are all going to be x, and the area is x squared. So I think that's actually, yeah, this would be a good example. So what I'm going to do, I'm going to start with perimeter increasing 1 inch per minute. Well, perimeter is equal to 4 times x. So I need to take the derivative of this equation implicitly with respect to t. So the derivative of p with respect to t is dp dt. And the derivative of 4x with respect to x would just be 4. But with respect to t, it's going to be 4 times the derivative of x with respect to t. Okay? And, well, they said that the perimeter is increasing 1 inch per minute, so the rate of change is 1, is 4 dx dt. Okay, well, I don't really know what to make of this, besides I think I should probably solve for dx dt. Right? And then, okay, I want the rate of change of area, so I should probably start with the area formula. Area is x squared. Take the derivative with respect to time, and that's 2x dx dt. Okay, and 2x for the derivative of x squared. Take the derivative of the outside, leave the inside the same, and then take the derivative of the inside for the chain rule. And that's me taking the derivative of x with respect to t right there. Okay, so now, at the time when x is equal to 2 inches, dA dt, which is kind of that's the rate of change of area with respect to time, is going to be 2 times dx dt is 1/4. So it appears that the area is increasing 1 square inch per minute. Okay. Now we can definitely do some more advanced related rate examples, and if you're interested in that, just go back to my channel and look at, related rates examples, more related rate examples, even more related rate examples. I've got a lot of them on my Calculus BC and my Calculus Examples playlist. Okay, but I think that's going to be all for this video. This is just a quick reminder of what we did in Unit 4.